So here at the bottom of the first page, we're going to take a look at some vocabulary, domain, range, set notation, along with some symbolic forms, and we'll continue that on to the next page as well. Okay, so set notation uses what I call squiggly brackets, those ones that look kind of like a parenthesis, but they aren't quite. It uses less than, greater than, less than or equal to, or greater than or equal to, and commas. And there are times where these particular symbols are appropriate and used. First situation, which is the first bullet there, a specific short listing of numbers. If you just have a specific listing of numbers, we use the squiggly brackets and commas. So for example, this squiggly bracket on the left, 3, 7, 10, 56. What that means is that there's a situation that a person is looking at, and those are the only possible answers, 3, 7, 10, and 56. It's a particular listing. It's a set of listing. So if I were to ask each of you, what type of vehicle did you drive in today, and we listed those types of vehicles, we would separate each one of those with a comma, and we would write it with the squiggle brackets around it. Okay, the second situation is a span or infinite listing of numbers. When that happens, use one or more of the less than, greater than, less than or equal to, or greater than or equal to symbols. And an example is y is less than 5. So we used some of the less than symbols when we were graphing last time. I want to come down to the next page, look at problem 4. In problem 4, right above it, it says, write the meaning of each of the following statements out in words. I just want us to get familiar with what these are. So in number 4, we see x, a greater than sign, and then 5. So in words, this would mean x can be all values greater than 5. And that's what I'm going to write out in words. X can be all values greater than 5. We assume that includes decimals and fractions and square roots. Problem 5 has the number first, the symbol, and then x. What we need to do is we need to flip that all over so the x comes first. We would write it as x is less than or equal to 3. It makes it a lot easier to interpret the values that x is going to take on. So in this situation, because we have the equal to, x can be all values less than 3 or equal to 3. That'll include negatives as well when we say less than 3. Problem 6. We see that we have a number -7, a less than sign, an x, a less than sign, and then a 9. When this happens with the variable being sandwiched in the middle of two less than signs, it's telling you that the value for x is anywhere between -7 and 9. But it doesn't actually include -7, and it doesn't include 9. Okay, so x can be anything between -7 and 9. We want to remember that there are decimals that x can be on problem 6. So x could be the decimal 8.99999. It's really close to 9. It's not quite 9. So it's okay for x to be any value that's really close to the -7 or really close to the +9. Okay. All right, problem 7. Very similar to problem 6, but this time you'll notice that there are equal to signs under this. So when I read this particular problem, I know that x can be any value between 2 and 4, or it can be 2, or it can be 4. It can be absolutely equal to 2, equal to 4, or anything in between. So x can be any value between 2 and 4, or it can equal 2 or equal 4. Of course, it can't equal 2 at the same time that it equals 4, hence we use the words or. Okay. Now, all of that is a precursor to being able to write our domains and ranges correctly. Well, it helps to know what a domain is. First of all, a set of ordered pairs is called a relation. So last unit, when we were graphing a whole bunch of ordered pairs, those are relations. Secondly, a domain is the set of x coordinates. We identify the domain for the relations below. Let's go ahead and do that right now. So I took a picture of a textbook just to give us 3 different situations. In this picture, you can kind of see there's 3 tables. On the left, it's labeled area of a square, and it says y equals x squared. So for the domain, we have to think, what values can x be? Well, in this picture, x is labeled as a side of the square. So we know x is a side of the square. And what values could a square have for its side? Okay, so x could be anything. What could x not be? Okay, couldn't it be a negative number because we're talking about a square? What else can't it be? It actually can be a decimal. I know they're not that much fun, but a side can be a decimal. And it can be a fraction. But it can't be 0. All right, so now we've identified what it can't be. So instead of saying x can be anything, we now have ruled out it can't be negative and it can't be 0. So x is any positive number, right? So the way that we can write x as any positive number is we write x is greater than 0. Meaning it could be a decimal, fraction, or square root. The second image in our table, you can see that it has an x-axis, a y-axis, and then there's a diagonal line. And we're wanting to look at that diagonal line that happens to come from the equation y equals x plus 2. So we need to use our skills from last unit to think about this particular line. This particular line we can see has arrows on it that go forever. And if we were to have created, we're not going to create it, but if we had created a table of values, what numbers could we use for x? Anything. Now last time we tended to use things like -2, -1, 0, 1, and 2, but it could really be anything. We just chose convenient numbers. And we can see that x can be absolutely any number because if we follow the blue line, the diagonal line, all the points on that diagonal line are filled up with ordered pairs that could be decimals, fractions, positives, or negatives. So on number 9, where it's the equation of a line, our domain is written very uniquely. It's written with a parenthesis. And actually, this is set notation. My apology. No parenthesis till tomorrow. It's going to be simply written all real numbers. Now, if you get tired of writing those 3 words, mathematicians have also created a sign that stands for all real numbers. It looks like a paragraph sign, but then you put a stick on it for R, all real numbers. Okay, so either one of those for your domain. Number 10. Number 10 is a scatter plot, and on the top of that scatter plot we see the title Online Advertising Revenue. On the horizontal axis we see the years 2006 through 2010, and on the vertical axis we see the label dollars in billions. In the actual scatter plot we see 1, 2, 3, 4, 5 points that are not connected by a line. There are 5 distinct points, and because they are 5 distinct points, we cannot assume that there's a data value for somewhere in between 2006 and 2007. We also cannot assume there's a data value between 2007 and 2008. Instead, we have to think, what are the X values of those 5 ordered pairs? So I'm going to take a look at this very first ordered pair simply because it's easy to write by. And if we were to describe that particular point, it would have the X value of 2007, and it would have the Y value that I will approximate, because it's not exactly equal, of 20. We could go through and we could list all 5 ordered pairs. And we could observe the X value of all 5 ordered pairs. What would those X values be? They would be the year. What years are they? That's right. 2006 to 2010. Now, I can't just write 2006 and then the word 2010, because there's partial years in between there. What we have to do is we have to actually list every single year in a list format. No. Think about programming. If you told it was a range of numbers from 2006 to 2010, it could use partials in there.
But they do have a range function.
They do have a range function, which would also, you'd have to limit it to make sure that it was just integers. And so what we're doing is we're forcing it into integers. Right. Okay, now on the same table, I want us to take a look at the next vocabulary word. The next vocabulary word, if I scroll back up, is range. Range is a set of all Y coordinates, Y values, the results. So we're going to go back to the same pictures, and we're going to say what the Y values or the results could be. So if we're thinking about area of a square, we've already identified that the sides of a square have to be greater than 0, any positive number. Remember, area is side times side, which is the equation up there, x squared. What values can area take on? Why do you say anything greater than 0? Good. Can't have an area of 0, or else the sides are just 0. And we can't have a negative area, because we're not working with negative space. Okay. So this is our range. Notice I use a Y value for our range. Okay. Coming over to our equation of a line. If we had plotted that line, our Y values would have been found in the table, but those Y values, if we make our table really big, could have also been all real numbers. Okay. So the range on this one is also all real numbers. And just in case you want that table, I'm going to quickly fill it out. Okay. So we can see that the table values look like they're all positive numbers except 0, but remember we actually could have created a table for decimals, fractions, and lots of negative numbers. Okay.